Good topic, Mike.
And you're still muted, Mike.
There we go. Sorry about that. Get my mouth working before I get the mechanics working. Um, and let me go. I have one other stupid thing popping up here on the screen. Kill that. Okay. Um, so much of the stuff that I end up popping up with, and as far as programs and stuff, are turn out to be actually real life situations where I'm helping out some other ham or someone's asking me a question, or I just kind of unwittingly wander into something. And I've recently come up on several instances, both with someone buying a kit for an antenna that had for VHF UHF that had some really pretty good gain to it. But in that kit for the antenna, they provided coax, so an RJ58. I think everybody probably knows what that is, which is basically junk coax for that kind of frequency. And people don't always understand the correlation between frequency, the type of coax, the type of antenna, how much loss you can incur with your coax, how it fits in the grand scheme of things as far as your effective radiated power. And people just don't always understand how everything kind of fits together and how that coax is such an important part of your antenna system. You can have a great antenna out there, but if you don't have the right coax for it, you may not get the performance you really want to have. So let's get into this guy. Uh, how come? There we go. I just have to have the right screen turned on. So we're going to talk about how coax affects the overall station performance, how it affects power output and receive signals, different types of coax. There are lots of different kinds of coax. When you go shopping for coax, it's not one size fits all. You have to think about the application of how you're going to end up using it. The importance of knowing what is between your antenna and radio, and that's that coax, that feed line there. So I'm not going to be talking about twin lead or ladder line or anything like that. That's a whole nother program by itself. We're just going to be talking about coax. And for ham radio operators, that's always 50 ohms, period, 50 ohms. We got other kinds of coax that are similar to it, and that doesn't always match up to what we're trying to do. So we always want to converge on using 50 ohm coax. So coax was invented back in 1929, first commercially used in 1941. Guess what? That's about the time when good old World War II was going on. So World War II was the first significant use of coax. Um, Before they were always using ladder line to feed antennas, and ladder line is pretty sensitive to if anything rubs against it, touches it, or if it's up against or close to any metal objects, it kind of negatively affects ladder line. So it's not always a good way of using it. So after the war, guess what? The ham radio operators had a plethora, huge supply of cheap coax, and good old ham radio operators, swarmed to the um, shops where they were reselling all this old communication equipment that was coming out of World War II. And so everybody loved this 50 ohm coax, and that became our standard for a long, long time. So here's what coax is made out of. You have a big black sheath, or usually it's black. I guess if you talk to Anna, you can get some custom colors for the outside plastic jacket. Then underneath that jacket, you have some kind of a metallic shield. Sometimes it's just braided wire, sometimes it's foil, sometimes it's copper cladding, but you have some kind of metallic shield in there that traps or keeps the RF inside that cable. You have a dielectric, that can be a different kind, all kinds of different kinds of plastics. There's good plastic, there's bad plastics out there, and we'll talk a little bit about that. And then on the very, very inside, you have a chunk of wire that can be just a solid strand or it could be a multi-strand wire. But in between that metallic shield and that center wire, that is what traps the RF. It has to stay inside of there. So off to the right there, we got a couple little pictures of different kinds of coaxes, different kinds of dielectric. The second one down is using a foam core, and most of the industry has moved away from foam core. Foam core dielectrics is kind of taken on a negative connotation where it's a guy that will soak up moisture very easy, and it will be a big spoiler for the inside of a coax there. Also, it doesn't like getting heated up. So if you're running some big power or you're running coax outside where you have a lot of heat, that foam core can move around inside or can move around a bit and allow that center conductor to touch the shielding in there, which is a bad thing. It creates a short. The one on the very bottom there that has that brown shield on it, or brown coating, you kind of look at that. There's not a whole lot of shielding in there. That reminds me of stuff that you used to buy at Tandy Corporation, Radio Shack. Whenever you buy that good old RG58, you open it up and it's like, man, where's the shielding in that? So it's really, really cheap. You want lots of shielding, lots of braiding in there. You want lots of if good old uh, copper foil or some type of foil in there, something that really, really traps the RF inside that. If you don't have a lot of that shielding, it allows that RF to escape out of that and allows other things to happen there, but it's not good. So, so some of the things that affects performance of coax. So one of the basic principles is the longer the run of coax, the greater the loss, and that loss is generally due to just plain old resistance. Good old Ohm's law. The longer the cable, the more losses you have. So it all gets down to the bigger the center conductor, the more shielding, the bigger the shield on that thing is, the better ability it is to conduct just current, and then you'll end up with less losses there. Now, the other thing that ends up biting you is frequency. As the frequency goes up, so does your losses go up. You find like down in the HF band, frequency doesn't bother you too much until you get up to about the 10-meter band, around 30 megahertz. From 30 megahertz on up, that frequency plays a big part in what you have for losses inside that coax. So one thing to remember is because of reciprocity, equal amounts of signal is lost on the transmit, on the receive. So we'll be talking about mostly losses on the transmit. So if you're losing 3 dB on your transmit because of losses inside that coax, you're also losing 3 dB on the receive side. So you're losing it both on the transmit and the receive side. So this is the only piece of uh, hard stuff that are actually little math in here. Um, but the only thing to really be concerned about is maybe taking a look at that very last piece of the equation there. So 3 dB of loss equals 50% efficiency. So that's a loss of 50%. So if you do anything tonight, remember 3 dB equals 50% loss. It also means that if you have gain of 3 dB, that means your output is going to double. And that only happens in your antenna. That antenna is the magic thing. That gain in that antenna is the magic thing that multiplies our output power. So we look at the equation, we look at power in over power, or power out. Actually, it's power in over our power out. So if you have basically power in is 50 watts, excuse me, 100 watts, let's say 100 watts, and you have a 3 dB loss, you're only going to get 50 watts out. So that, looking at that equation, you can tell exactly what is going to happen with your power. So let's take a look at some examples. 100-watt transmitter transmits with 6 dB of coax loss. And let's say your antenna doesn't, well, we're not even going to talk about the antenna. So you have basically at 6 dB, you're only getting 25 watts out of that piece of coax. 100 watts in, 6 dB of losses, 25 watts coming out. So that little chart over on the right, you can, uh, most of your systems are going to have something. I'll just say as a general rule, I personally try my best to keep my losses under 2 dB, something less than 2 dB worth of losses. But still, that means that only 65% of that signal is getting in or out of that coax. You see at 3 dB, 50% loss. See at 6 dB, that's only 25% of that signal getting out of it. At 9 dB, and believe me, there are coaxes. When you start looking at that good old RJ45, excuse me, RJ, excuse me, with good old LMR, excuse me, not, I'm getting all confused here. Excuse me about this, but good old um, RG 58 ohm, 58 coax. You're going to get at running at the UHF frequencies, so running up in that 4 to 500 megahertz area. You're only going to get 2.5 watts out of that thing. Really, really bad. So let's take a look at some coaxes here now that I've boogered up RG58. So RG58 is usually okay to use. Now it won't handle power, but up to 10 meters, you can at least contain the losses to about 2.5 dB, so a little bit less than 50%. 50 megahertz, a whole lot more, 150, a whole lot more there, but not quite, um, 25%. Take a look at 400 megahertz. 400 megahertz is when where that 70 centimeter band sets, 440 sets. And you can see there we're up at 10.4. So we're just getting pittance out of that piece of coax. So anybody, if you know anybody that's a new technician, just got a new antenna and they're trying to do stuff on 2 meters and 440 and they're running RG58, you might give him a friendly hand and letting him know that that might not be a good idea with a 100-foot piece of coax there. So RJ8X is an improvement over 58. Another one that's kind of a favorite of mine, and that's when I'm out camping, rather than running big heavy coax around, and I'm usually on HF anyway on that. I like using the LMR 240. That's a quarter-inch coax, and you can see that with fairly small amount of losses there. Then you get into the RG8. The RG213 is a very good coax because of the shielding and stuff. It doesn't seem to perform all that much better, but it still is a good heavy duty coax, and it's also pretty flexible too. Um, the 9913 is a unique coax on how it's built on the inside, and it's a little bit more, much more expensive, but it has some pretty darn good specs. Then you get up to things like LMR 400. That is a really stiff coax, but look at the specs on that. Even down on HF, I mean, very small amount of losses, all the way up into the 400 megahertz. You can still keep your losses down below 3 dB, which is pretty darn good. Now, if you really have the extra money, um, there's LMR 600. It has even better specs. And I have had to use the LMR 600. I put in a cell phone repeater in the house, and my antenna was up on top of my tower, and I had to get that little tiny bit of RF all the way off my tower, all the way down into the house. And I looked and looked and looked at trying to find something that didn't have horrible losses. And the best I could come up with outside of using hardline was good old LMR 600. And it did very nice, but extremely expensive. Extremely expensive. Connectors are quite expensive for that, but it worked very, very nice. Okay, so here's another cool chart that kind of shows the effective power. This is actually showing things in dB. So you have the loss and the amount of power you get out per 100. And you can kind of walk through it and see everything kind of matches up. Um, you can see real quickly that you sure don't want to use that RG58 when you're running up on VHF and UHF frequencies. The losses are staggering. And so the some of the things that really affect the cost of coax, and that's that darn braiding, the type of braiding that they put on there to keep the RF inside that coax. Is one of the major parts of coax. So you got things like tin copper, you can have conductive foil, you have aluminum foil. They even have copper foil on the inside of that, or a combination of foil and braiding that they have in there. Most of them I'm seeing both foil and braiding that are in there, but it's that's one of the main thing that drives it. So higher percentage of coverage, the more effective the shield is. In all the specs on your have for coax, it'll tell you how much coverage each one with it, that you have with that. So if you can get closer to 99%, the better you are as far as effective coverage of your shielding. Um, let's see. So, yeah, and on the return path, everybody knows that that shield there provides the return path, and will eventually provide the return back to ground. So, general bending radius. So, coax is one of those things you just don't want to bend at a 90-degree, putting around the corner. If you do that, remember that there's a bunch of plastic on the inside of that. And you're going to, when you bend it real sharply, you're going to break up the shielding on the inside. You also are going to mash together that insulation on the inside. Even that outside covering is going to get stressed as you make really sharp turns. So as a general rule, you don't want to go to more than about 6 times the radius of the diameter of the coax. It's really more or less recommended that you keep it at least 10 times. So the better recommendation, I like 10 times. I'm always very, very cautious on how I bend that coax and how I bring it into the house and how I'm trying to mitigate any kind of damage from any kind of rapid turning. So there are coaxes out there that have multi-strand interior, then the braiding is really loose, really heavy braiding, and it allows for better turning. And you'll see when you look at specs on that 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 coax is made for more severe bending, like that LMR 400 that I talked about. There's also a Superflex model of that that gives you some really good turning radiuses. So that is the kind of stuff you want to put around a rotator. So if you're going up a tower with LMR 400, before you hit that rotator, you want to change over to Superflex so it can handle the constant flexing of that center conductor, the foil on the inside, and the insulation. So let's look at some costs. Good old RG58 you can get for anywhere from 20 to 35 cents a foot. So these prices I got from are off of DX engineering sites. And so, of course, they're always more expensive than everybody else, but they usually have good quality coax there. So you can find stuff cheaper than that. That LMR 240, a buck to a buck 30 for that. The 213, about a buck 60. You can see that 9913 because of the internal construction of that coax. It has a huge adder for that. The LMR 400, most of the prices you're going to find are almost in that $2 category. You can find stuff cheaper down in that dollar 60, dollar 70 area. Now there's a lot of Chinese or knockoff LMR 400s. You have to be really careful on when you go buying that stuff to see that it really works the way it is. I did buy recently 100 foot of LMR 400 and I threw it up on my spectrum analyzer and it was within 1/10 of a dB worth of loss of where it was supposed to be compared to the LMR 400. And that kind of air there, you can get that on couplers and other things that can produce that kind of air. So that coax was it was basically spot on the money for losses. So moisture is one of your big bad guys that you want to be careful for. The sheathing on the outside of coax is not always rated for 100% moisture. They got the sheathing can be rated for direct burial, stuck in the ground, submersible, a bunch of different things. But generally, for anything that I buy around here, I try and make sure that it has the ability to handle uh, dropping the coax in a lake or water all the time because it just rains too much. And I just prefer to make sure I just don't have any possibility of moisture getting into the inside. When it gets into the inside, it rusts up and it screws up all that shielding on the inside and renders that chunk of coax not usable. So, believe it or not, coax does have a finite lifespan. Most of it, and this is, I think this slide's probably a little bit dated, but most of your coax will usually pretty easily last you 7 to 10 years. The better stuff that you buy these years, like if you maybe buy some Chinese stuff, you're probably going to get it with 7 to 10 years out of it. But if you buy like the Time Warner, the better type of coax, it'll last longer. So, how do you know when it's fading? I'll tell you what, you really don't know because it fades very gradually over time, and you just don't really know it unless you disconnect the darn both ends of the coax, run it up on a spectrum analyzer, and see what the heck is doing for you. But you'll notice that your signals seem to have faded a little bit. Your SWR seems to be higher than what it should be. Unable to get maximum performance out of your transmitter, where you just seems like the SWR is high enough where no matter what you do, you just can't get a good match out of going to antenna. Even sticking a dummy load out of there, you still can't find it. So take the coax, connect it up to a good old VNA spectrum analyzer, see what your real losses are, and see if your coax has gone south on you. Then it's time to replace it. Total system performance. So the way we look at our system as far as performance, so that includes our antenna and our coax. And we want to figure out how much power is actually going to get rated out of there. And believe it or not, the good old coax, it will always give you losses. It can never give you a positive bump up. Your antenna on the other side, yeah, it can give you it can give you losses, but it can also give you a heck of a lot of gains. So example for calculating ERP, you have your transmit output power times your system gain. Your system gain is made up of your feed line losses plus your antenna gain. And um, so anyway, your antenna gain. So quick little example, transmit power of 100 watts, coax losses of 2 dB. That sounds pretty normal. You have an antenna out there that's giving you about a 60 dB worth of gain on a particular frequency, particular band. You can't make just a big long generalization on what that gain is. It has to be in context of what the frequency that you're operating in. So that nets you a system gain of 4 dB. So that's a plus 4 dB. So the next step is converting that 4 dB into ERP. So we're always assuming that we're running 100 watts. That will yield you 250 watts. So that 4 dB gives you a big plus. And remember, the reciprocity there, so it's reciprocal. So it affects the same thing on your transmit, affects you also on the receive. Big important thing. So here's a goofy chart that I really should have turned this backwards and looked at the losses there. But the context here is ERP. So if you can get a net gain of one, and actually one will give you 126 watts out of the 100 watts. So that's both the losses you have in your feed line, and this is at feed line plus your antenna. So your antenna probably has a 2 or 3 dB worth of gain in order to get that 126 watts out of it. And the all important one there is the old 3 dB. So if you keep thinking of multiples of 3 dB, that will give you an ideal of how power gets multiplied every 3 dB. So you have 3 dB, 200 watts, 6 dB, um, uh, 400 watts, um, 9 dB, you're at 800 watts, 12 dB, you're up at 1585 watts. So you can get the idea that in multiples of three, you can kind of estimate what you're going to end up getting as far as a net gain out of your ERP by every 3 dB. So what things to consider when purchasing coax? You want to think about what frequency. Is this going to be used on HF? Is this going to be used on VHF or VHF and UHF? But if it gets used on UHF, you better pay attention to what your feed line losses are going to be with that kind of coax. What is my acceptable dB losses? You have to set that for it. And it's always a relationship between cost and what you want is not always what you can afford. But me, I like no more than 2 dB worth of loss. And so that usually drives me into on uh, the, the higher bands, the higher frequency bands into LMR 400. Does the coax need to be flexed? Should be ED. So if it's going to be moving around a whole lot, like going around a rotator, then you need to select the right kind of coax that has the flexible insides to it. Will the coax be buried in the ground? So I mean, a lot of coax out there is made where you can dig a trench, shove it in the ground, but you want to end up make sure that you purchase a direct burial of coax that has the right kind of sheathing on it that won't absorb the moisture. Of course, everything coax is always has to be UV resistant. I have no idea if pink colored coax what the UV rating is on it, but it needs to be pretty good for around here. So water intrusion, types of jackets and dielectrics, all your connections and everything need to be sealed up if you're going to end up having any of those connections outside. Carefully check specifications of the coax. So you always want to go back, find the spec sheet, read through the specs, and understand what those numbers mean before you end up making the purchase. It means it's a little technical, but at least you know exactly what you're buying when you're to pull the trigger and purchase things. Finally, the cost. How much am I willing to pay for the coax? And don't be cheap. Please don't be cheap. Buy the good stuff, and you'll be pleasantly surprised, or you'll be real pleased with the purchase because it lasts you many years and give you good performance. So that's it. and I will give it back to, come on, how do I get it back here?
Before you stop sharing, Mike,
Yeah,
could you
okay.
go could you go back to that chart where it showed the price per foot? I think it was like slide 9 or 3. I can't remember.
Okay.
And it was talking about the LMR 400 being actually cheaper than something that performed less. And is that because of the
Yeah.
flexibility?
No, it's just that LMR is becoming a better price point. More people are using that.
Yeah, that's it right there. Cost per foot.
Yeah.
Yep. Okay. No, I was just
So
curious. It seemed like an obvious answer right there.
yeah, yeah. I mean, it's because it's the good guys have always been that 99 213, the 213 RG 213. Um, the RG 8U is kind of it's been good, but it's a little long in the tooth. But the better ones have always been that, like a lot of people have gone with RG 213, and anymore because there are when when the original LMR was produced out there, LMR 400, it was very expensive, and the price point it really hasn't changed. Now, what's happened is you have a whole lot of other knockoffs coming into the market, which has caused that LMR 400 to end up moving down in price.
I see. Thank you for the clarification.
Just a
You're
quick
welcome.
comment, Mike.
Sure.
Um, if you can find a reasonable price on LDF2, which is 3/8 inch hardline, the
Hmm.
connectors for RG8 will fit on LDF2.
They
So
will.
yes, and you can solder them on, just like you can with 8U. So if you get those connectors, you can save a lot of money in connectors, and you might be able to find the good thing about hardline like that is it lasts a long time. So even if you can
Yeah.
find some gently used stuff off of a commercial installation, 3/8 inch hardline can be reasonably priced used. And it doesn't have that much less loss than like LMR 400 does. But if you are
Hmm.
running a high power station where you are having RFI issues, um, because it is hardline, it is 100% shield, because
Yep.
the shield is continuous. So it helps you out with potential RFI problems you have. So
Hmm.
just a hint with that, if you can find if you are having problems with RFI and you can find some 3/8 inch hardline, the connectors fit and it can be, you know, it's going to be more expensive than an LMR 400, but it can still be reasonably priced. It's not like the, $5 or $6 a foot I paid for my 7/8 inch card hardline.
So what
And I
about
also
any
want to recommend
downs?
that, I'm sorry, go ahead, Mike.
Go ahead.
I was just going to say, we also know a repeater owner in our club, Chris, AB7BS. Feel free to reach out to him on his Facebook page and ask him if he has some of that wonderful feed line available. He might be able to locate it for you.
I have a stash of some 3/8 inch and a half. A half I'm not willing to give up because that's going to go for my 440, a bunch of my 440 equipment. But, you know, I may be able to be sweet talked out of some 3/8 as long as, I have appropriate lengths. But we would have to talk about that.
So what are any of the downside on hardline?
It's hard to work with, right? I mean, you're not going to bring it out to 7QP to throw up in a tree and stuff like that. It pretty much has to go to some place that is going to be fixed. If you're doing it with a rotor, you want to run it all the way up to the tower, but you want to put a socket connector on there because you want to run like a 1 foot length of, or 400 from the end of the hard line into the rotor so that you can get something that flexes. They do make half and 3/8 super flex. I don't think they'd make great rotor connectors though in there though. But anyway, um, yeah, that's the cost is the big disadvantage because if you say you're doing 7/8 inch hard line, I think the connectors cost me new. They're at least $50 a piece just for the connectors on the end. Again, sometimes you can get some that are in good shape that are gently used. They're not solder on like a flexible coax is. They kind of screw together, so it's easy to salvage the connectors off of hardline, as opposed to, having to unsolder something. So you can find some, decent looking ones that may have been gently used, especially the inside end of that connection. But yeah,
Hmm. So those connectors are approaching the price of the connectors you use on the LMR 600.
yeah, yeah. It's not hardline is not cheap. It's an investment, but again, generally the hardline will last you a real long time because it's tough stuff.
Yep.
You do have to watch out for water intrusion, but I think the cost is the biggest disadvantage. And, again, secondly, it's kind of hard to work with. So count on spending some time threading it through wherever you need to on your house and battening
Hmm.
it down. It's also heavy, right? So you have to
Yep.
count for that weight when you're counting on your tower weights and things like that, because your hard line could be a significant chunk of that.
Yep. Any other comments out there?
Thank you, Mike. Thank you, Anna.
Just remember 3dB.
All right, Mike, always something valuable we can all learn, and I do appreciate all of the effort that you put into presenting all of this wonderful wisdom.